Well, hello to my honors physics students. I miss you guys already. I'm sure you miss me too. I'm going to start by going over some of the stuff that you all saw in lab last week, right on the last day of class before we had to say see you later. I'm going to try to stick with only the important stuff. In other words, the things that you're most likely to see in college, the things that you're most likely to see on the final exam, and I think you'll notice that the WebAssign kind of sticks to the same idea. So if you think back to the lab that you did on the last day before we left, you all were sprinkling iron filings on a piece of paper with a bar magnet underneath of it, and you were investigating how those iron filings lined up with the bar magnet. In other words, you were visualizing the shape of the magnetic field. Those iron filings ended up looking something like this. In the same way that we draw electric field lines going from plus to minus, you'll notice that with magnetic fields, we always draw the magnetic field line going from north to south. The second thing you did was investigate what happens when you put two bar magnets near each other and again visualize the magnetic field using iron filings. You get something that looks like this. On the opposite ends of these two magnets, you find that the magnetic field looks more or less like it did with the single bar magnet case. What is interesting is what happens in the region between the two bar magnets. You end up seeing a field that looks a lot like these two make their own north and south. Later on, when you hear me talk about uniform magnetic fields, you can kind of think of the region in between these two magnets as a place where the magnetic field is pretty uniform, meaning it's got pretty much the same strength everywhere, and the field points in more or less the same direction. On the other hand, when you put two bar magnets near each other and have their opposite poles facing, the first thing you probably noticed was that if you put them too close, they start to repel each other, just as if you put these two close, they started to attract each other. But if you can get them the right distance apart so that they won't push each other around, then you see once again you see that once again, the field surrounding the edges of the magnets looks pretty much normal, the same way as it does up here. However, when you put the two like poles near each other, just like electric field lines, you find that these lines can't cross each other, so they end up sort of bending away. And you get a strange region in between where the iron filings really didn't show up at all. By the way, I'll make this little symbol a couple of other places to show you that this is a question that you can expect to see on the final exam, if you ever end up taking that final exam. One important thing to remember is that a wire that carries current is a magnet. Also, magnets will only exert forces on other magnets. This reminds us that compass needles are just little magnetized pieces of metal, and because they are aligning with the Earth itself is also acting as a magnet, a giant magnet. One interesting side note to this is that because south poles of magnets attract north poles of magnets, in other words, opposites attract, and because the north pole of a compass needle aligns with the north pole of the Earth, that means that the Earth's magnetic south pole is actually up in the north. This sort of thing is kind of confusing, so you don't have to worry too much about it. I just think it's kind of interesting that magnetic south and geographic north are both in the same place. Therefore, if a wire that carries current is a magnet, and magnets only exert forces on other magnets, then if you put a magnet near a wire that carries current, the bar magnet will exert a force on that wire. So what I invite you to imagine is that you take some sort of power supply or battery or whatever it might be, and you set it on a table. You attach some wires to the battery so that current flows down towards the ground and then returns back up to the battery. And in the space in between where the wire hangs down toward the ground, you've produced a magnetic field between a north and the south pole of a magnet. You could achieve this by holding two bar magnets there, sort of like is shown here, or you could get away with it by using a single horseshoe magnet. Just kind of imagine the horseshoe magnet curves around like this. Sure enough, if you do this, and I was really hoping to show you this in class before we left, but I just didn't have enough time. If you do this, you notice that the wire moves. The strange thing is that the magnet doesn't move this way, and it doesn't move this way. It moves perpendicular to both of those directions, perpendicular to the field direction and perpendicular to the current direction. The field direction is along the x-axis horizontally. The current direction is along the y-axis vertically. That means the only way for this wire to move perpendicularly to both of those things is for the wire to move either this way or to move that way into the page. In this particular case, what you find out is that the wire does move this way. So at this point, it'll be useful to talk about how we draw three-dimensional stuff like this on a two-dimensional piece of paper. The idea here is that you have to imagine maybe an arrow or a dart being thrown away from you or towards you. If you had a dart that was moving towards you, then the first thing you would see would be the point, the tip of the dart. So we draw just a single dot to imagine the tip of the dart. On the other hand, if the dart or the arrow is moving away from you, then you would see the feathers, the flight, the back part of the arrow or the dart. So we just draw a little X to show a direction that points into the page. So in this particular case, the force on the wire will be directed out of the page. There's a little visual trick to help you figure out and predict what this direction will be. It's called the right-hand rule, sometimes abbreviated just RHR. I'm going to demonstrate this right-hand rule with several examples, and what I'm going to do in each case is I'm going to draw the current using blue, I'm going to draw the magnetic field using green, and I'm going to draw the force using red. So with the right-hand rule, what you do is sort of make an X, Y, Z coordinate system out of your first three fingers. This could be the X, this can be the Y, and this can be the Z. Some of my AP students will call this the physics gang sign. So when you're using the right-hand rule, you make your thumb point in the direction of the current, you make your index finger point in the direction of the magnetic field, and you make your middle finger point in the direction of the force. In this example, the current pointed down, the magnetic field pointed to the right, and so the middle finger points up towards you out of the page.